For the unit Thermodynamics, in previous lecture we discussed enthalpies of physical changes including enthalpy of fusion, enthalpy of vaporization and enthalpy of sublimation. Hess's law of constant heat summation, applications of Hess's law, determination of lattice energy and influence of temperature on the heat of reaction or Kirchhoff's equation. In continuation to this, today we are going to discuss the experimental measurement of heat of reaction through calorimetry, including constant pressure calorimeter and constant volume calorimeter, bond energy and applications of bond energies. Now we are starting with calorimetry. Calorimetry is the study of heat flow in physical or chemical changes. The apparatus which is used to measure this heat is known as calorimeter. A typical calorimeter includes a thermometer to measure the temperature changes and a medium to transfer the heat and some insulating system such that we can slow down the thermal equilibrium process so that the temperature changes can be measured easily. There are two types of basic calorimeters, constant pressure calorimeter and constant volume calorimeter. First, we are going to discuss the details of constant pressure calorimeter. The system is open to air and the pressure is kept constant at atmospheric pressure. A thermometer is used to measure the temperature change. Water in the coffee cups or the aqueous solution is the medium into which or out of which the heat is transferred. The water and the system are insulated from the rest of the room. Some sort of lid keeps the heat from leaking out too quickly from the top of the calorimeter. In a typical experiment to find the heat capacity of some solid substance, a heated solid substance is added to the cold water in the calorimeter. The hot object acts as the system and the cold water and calorimeter as surroundings. The heat lost by the system is equal and opposite in sign to the heat gained by the surroundings. Here surrounding is cold water and the calorimeter. Normally water is used as a system because it is safe and easy to use water, as it has a constant heat capacity of 4.184 joules per gram per degree Celsius. Sometimes it can be confusing to the students though, because water is also used as a medium in the coffee cup calorimeter. Suppose we add 50 ml of hot water at 80 degrees Celsius to 50 ml of cold water at 20 degrees Celsius. Now hot water will transfer heat to cold water. As we have added same amount of water, or we can say same mass of water, and specific heat of hot water and cold water is same. So the temperature change for hot water and cold water must be the same. If the calorimeter was a perfect insulator, we would end with 100 ml of warm water at 50 degrees Celsius. But in a typical experiment like this, we would end with warm water at a temperature which is less than 50 degrees Celsius. Say it is 40 degrees Celsius. Then where did the extra heat go? Actually, this missing heat wound up the stirrer, the thermometer, the air inside the calorimeter and the material of which the calorimeter was made. The heat lost by the system would be equal to the heat gained by the surroundings. Here surroundings is the water and the calorimeter. Let us have an example. A measured amount, say 72 grams of hot water is added to a measured amount, say 78.1 grams of cold water in a coffee cup calorimeter. The data was recorded. Then what is the heat capacity of the calorimeter? The recorded data is initial temperature for hot water is equal to 82.9 degrees Celsius. Initial temperature for cold water is equal to 22.0 degrees Celsius and final temperature for the mixture of water is equal to 44.1 degrees Celsius. Now, heat for the system will be equal to minus heat for the surroundings. Surroundings is water and calorimeter. So, Q system will be equal to minus Q of water plus Q of calorimeter. So, Q of system will be equal to mass of hot water into specific heat capacity multiplied by delta T for the hot water. This will be equal to 72 grams multiplied by 4.184 multiplied by 44.1 minus 82.9, and we will get minus 11700 joules. Now, you have to find the heat gained by the water in the calorimeter. This will be equal to mass of cold water multiplied by its specific heat capacity multiplied by change in temperature. So, Q of cold water will be equal to 78.1 multiplied by 4.184 multiplied by 44.1 minus 22.0, which is equal to 7220 joules. Now, Q of system will be equal to minus Q of water plus Q of calorimeter. Here Q of system is minus 11700 joules and Q of water is 7220 joules. Therefore, minus 11700 joules will be equal to minus 7220 joules plus C into delta T, where C is the heat capacity of the calorimeter. Therefore, C will be equal to 11700 minus 7220 divided by 44.1 minus 22.0, which is equal to 2.02 into 10 to the power 2 joules per degree Celsius. Hence, this is the heat capacity for the calorimeter. Now, if we use this calorimeter, we can find the heat capacity of unknown solid. Here, the water and calorimeter will be the surroundings and solid will act as the system. Solid has to be heated to some known temperature and it is to be added to the water in the calorimeter. Let us have an example here. A weighed amount of metal is heated in a water bath, quickly dried, then added to a coffee cup calorimeter. The lid was replaced and the water stirred. The highest temperature was noted. Now, what is the heat capacity of the metal? The recorded data is for metal mass equal to 135.7 grams, initial temperature equal to 99.5 degrees Celsius and final temperature is equal to 32.4 degrees Celsius. For water, mass equal to 145.9 grams, initial temperature equal to 22.2 degrees Celsius and final temperature is 60.7 degrees Celsius. And for calorimeter, specific heat capacity of calorimeter is equal to 2.0 into 10 to the power 2 joules per degree Celsius. Initial temperature is equal to 22.2 degrees Celsius and final temperature is equal to 32.4 degrees Celsius. Now, Q of system will be equal to minus Q of surroundings. Here surroundings is water and calorimeter and the system is the hot metal. We know all these variables except the specific heat capacity of the solid. So, substituting all the values in the equation, we will get 135.7 grams multiplied by specific heat capacity of the metal multiplied by delta T for the metal, which is equal to 32.4 minus 99.5 equal to minus 145.9 multiplied by 4.184 multiplied by 32.4 minus 22.2 plus 2 into 10 to the power 2 multiplied by 32.4 minus 22.2. Here on calculation we will get C, which is the specific heat capacity of the metal, equal to minus 8270 divided by 135.7 multiplied by minus 39.1, which is equal to 0.91 joules per gram per degree Celsius. Sometimes instead of heat capacity of calorimeter, water equivalent is given. Now, water equivalent is the amount of water that would absorb the same amount of heat as the calorimeter, per degree temperature increase. Now recall that according to first law of thermodynamics, change in internal energy is the sum of Q and W, means heat change and work done by the system or work done on the system. If the experiment is done on constant volume, then there is no work done of expansion, means W will be equal to 0. Therefore, delta E, that is change in internal energy, will be equal to heat change at constant volume. But coffee cup calorimeter is an apparatus to calculate the heat of reactions at constant pressure. If we want to calculate the heat of reactions at constant volume, then another type of calorimeter is to be used, which is known as Bomb Calorimeter. If we are using reactants and products in gaseous state, then there will be a change in volume and there will be some work done. Hence, coffee cup calorimeter is not enough to calculate the value at constant volume. The bomb calorimeter is an apparatus to measure the heat of combustions of reactants at constant volume. The reaction takes place in a heavy duty stainless steel cylinder called bomb. The bomb has a threaded lid so that it can be sealed. The reactants are placed in a pan that is wired to a high voltage power supply and sealed inside the bomb. A high pressure of oxygen is added to the bomb through a gas inlet valve in the lid. Because the calorimeter is designed to measure the heats of combustion reactions, the high pressure of oxygen gas ensures that there will be enough oxygen for the reaction to go to completion. The bomb is lowered into an insulated water tank that has a thermometer and a stirrer. A high voltage electrical current is sent through the chemical pan, causing the reactant to combust. The heat given off by the system is transferred to the stainless steel and water in the calorimeter. We measure the temperature change of the water and the calorimeter so that the heat capacity of calorimeter can be calculated before calculation of heat given out in a reaction. Benzoic acid is often used to find the heat capacity of bomb calorimeter because it is a stable solid which is easy to handle. For example, 1.7735 grams of benzoic acid are reacted in a bomb calorimeter. The temperature of the water bath changes from 22.11 degrees Celsius to 25.08 degrees Celsius. What is the heat capacity of the calorimeter? The heat of combustion of benzoic acid is minus 3228 kilojoules per mole. Now, Q of system will be equal to minus Q of surroundings, which is equal to minus C multiplied by delta T. We will get 1.7735 divided by 122.12 multiplied by minus 3228. Here 122.12 is the molecular mass of benzoic acid. Therefore, this will be equal to minus C into delta T. C is the overall heat capacity of the calorimeter. We will get C equal to 15.8 kilojoules per degree Celsius. After you determine the heat capacity of the calorimeter, you can find the heat of combustion of any of the substances. For example, sucrose has a molar mass of 342.3 grams per mole. 1.028 grams of sucrose are burned in the bomb calorimeter. The temperature rises from 22.21 to 23.29 degrees Celsius. What is the molar heat of combustion of sucrose? The heat capacity of the calorimeter and its contents is 15.8 kilojoules per degree Celsius. Q of system will be equal to minus Q of surroundings. This will be equal to minus C multiplied by delta T, where C is the overall heat capacity of the calorimeter. This will be equal to minus 15.8 multiplied by 1.07 equal to minus 16.9 kilojoules. As 1.028 grams is 0.003003 moles of sucrose, so the heat of combustion is minus 5630 kilojoules per mole. The combustion of sucrose is a chemical reaction with the reaction equation C12H22O11 plus 12O2 giving you 12 CO2 plus 11 H2O. As this heat of combustion is found at constant volume, hence it is equal to delta E. If we want to calculate the enthalpy of reaction, that is delta H, then we have to use the relationship delta H is equal to delta E plus delta N RT, where delta N is the change in number of moles of gases, that is number of moles of gases in products minus number of moles of gases in reactants. Now we will discuss bond energies and bond enthalpies. When some bond is formed between two atoms, then some energy is released and the same amount of energy is absorbed when the same bond is broken. The amount of energy required to break 1 mole of bond of a particular type between the atoms in the gaseous state under 1 atmospheric pressure and the specified temperature is called bond dissociation energy. For example, bond dissociation energy of hydrogen-hydrogen bond is 433 kilojoules per mole. For chlorine-chlorine bond, it is 242.5 kilojoules per mole. For hydrogen and chlorine bond, it is 431 kilojoule per mole. For iodine-iodine bond, it is 15.1 kilojoules per mole, and for hydrogen and iodine bond, it is 299 kilojoules per mole. The bond dissociation energy of diatomic molecules is also considered as bond energy. However, the bond dissociation energy also depends on the type of bond and on the type of molecule in which the bond is present. When a molecule contains more than one bond of the similar type, then the average bond dissociation energy is equal to the bond energy. Consider the dissociation of water molecule, which consists of two OH bonds. The dissociation occurs in two steps. In first step, H2O will dissociate in gaseous hydrogen atom and gaseous OH. In second step, gaseous OH will dissociate in gaseous hydrogen atom and gaseous oxygen atom. The average of these two bond dissociation energies gives the value of bond energy of OH. The bond energy of OH bond will be equal to 497.8 plus 428.5 divided by 2, which is equal to 463.15 kilojoules per mole. Similarly, the bond energy of carbon-hydrogen bond in methane is equal to 1/4 of the bond dissociation energy of CH4. For example, gaseous CH4 will dissociate in gaseous carbon plus 4 gaseous hydrogen, and delta H for this reaction is equal to 1664 kilojoules per mole. Now, bond energy for carbon-hydrogen bond will be equal to 1/4 of the bond dissociation energy of methane, which is equal to 1664 divided by 4 equal to 416 kilojoules per mole. Now, we will discuss some applications of bond energy. Bond energy data can be used to calculate the heat of reaction. Heat of reaction will be equal to the sum of bond energies of reactants minus the sum of bond energies of products. In case of atomic species, heat of atomization can be given in place of bond energies. Here is an example to calculate the heat of reaction with the help of bond energies. Calculate the enthalpy of the following reaction: CH2 double bond CH2, that is ethene gaseous plus gaseous hydrogen, giving you ethane CH3 CH3 gaseous. The bond energies of carbon hydrogen, carbon carbon, carbon double bond carbon and hydrogen hydrogen are 99, 83, 147 and 104 kilocalories respectively. The reaction is shown in this figure. You can see the number of carbon-carbon bonds, carbon-hydrogen bonds, hydrogen-hydrogen bonds and carbon-carbon double bonds in this representation. Delta H reaction will be equal to sum of bond energies of reactants minus sum of bond energies of products. Therefore, delta H of reaction will be equal to bond energy of carbon double bond carbon plus 4 into bond energy of carbon hydrogen bond plus bond energy of hydrogen hydrogen bond minus bond energy of carbon carbon bond plus 6 into bond energy of carbon hydrogen bond, which is equal to 147 plus 4 into 99 plus 104 minus 83 plus 6 into 99, which is equal to minus 30 kilocalories. When a compound shows resonance, there is a considerable difference between the heat of formation of the compound that is calculated with the help of bond energies and that calculated experimentally. Actually, the heat of resonance is equal to experimental or observed or actual heat of formation minus calculated heat of formation. Let's have a look on an example to calculate the resonance energy. Calculate the resonance energy of N2O from the following data. Delta H naught formation of N2O is equal to 82 kilojoules per mole. Bond energy of nitrogen triple bond nitrogen, nitrogen double bond nitrogen, oxygen double bond oxygen and nitrogen double bond oxygen bonds is 946, 418, 498 and 607 kilojoules per mole respectively. The equation will be as shown here: nitrogen triple bond nitrogen plus half oxygen double bond oxygen giving you N2O, which has the structure nitrogen double bond nitrogen double bond oxygen. Therefore, delta H formation of N2O will be equal to bond energy of nitrogen triple bond nitrogen plus half multiplied by bond energy of oxygen double bond oxygen minus bond energy of nitrogen double bond oxygen plus bond energy of nitrogen double bond nitrogen. That is 946 plus half into 498 minus 607 plus 418, which will be equal to 946 plus 249 minus 607 minus 418, which is equal to 170 kilojoules per mole. Now, resonance energy will be equal to observed heat of formation minus calculated heat of formation. Therefore, resonance energy will be equal to 82 minus 170 equal to minus 88 kilojoules per mole. In the end, let us revise what we have learnt today. We discussed calorimetry, including constant pressure calorimeter and constant volume calorimeter. We defined bond energy and applications of bond energies. And with this lecture, we come to the end of Thermodynamics I.